Okay, thank you for coming back. We are going to do an example of an inverse Laplace transform. So what this means is we are going to have a capital F function of S that we are going to convert back to its lowercase f of t function. So we are doing, obviously the inverse. We're working our way backward. This obviously takes a good knowledge of our Laplace transforms to begin with. So this will really require us to use our table and also a little algebraic manipulation to get this to fit a form that's in our table. So the first form of algebraic manipulation that we are going to see a bit of in this section is partial fractions. So I picked one right here, 2s over s squared minus 1, because we don't have a form of this in our table. And what we're going to have to do is take this function of s, and we are going to have to do the factored form of the denominator here, which is s plus 1, s minus 1, and we're going to review our partial fractions method here. So we're going to call this a, and we're going to call this b, and we're going to figure out what those numerators should look like to basically split this singular fraction into two fractions that we can do the inverse transform on. So method of partial fraction says we take this whole thing, we multiply by our lowest common denominator, s squared minus 1. So that way on the left side here, we eliminate that denominator altogether. On the right-hand side, distributing it here, it looks like I'll have a times s minus 1 plus b times s plus 1. And we have to solve for a and b. And so typically what we do here is go ahead and say, well, this is like having 2s plus 0. On my right-hand side of my equation, I have an as and I have a bs. I'm sorry. Which means I have a plus b times the quantity, or a plus b is the quantity times s. And then it looks like in terms of my constants, I have a negative a and a positive b right here. So I will have negative a plus b, which is equal to this constant of 0 over here. All right, so a plus b is equal to 2. And negative a plus b right here is equal to 0. You can definitely use the method of smart s's is what it would be in this case. I don't know if Miss Colleen worked with you on that method, where if I were to choose a smart value for s here, it would be one that eliminates my a term completely so that I could solve for b. You can absolutely do that. The reason why I chose to go this route and solve a system is because this is actually a pretty easy system to solve. So I can just add my two equations together here, eliminate the a's, and get 2b is equal to 2, which means that b has to be equal to 1. And if a plus b is equal to 2, then it must mean that a is also equal to 1. So that means that, bringing it back to my capital F function of s, I can rewrite this as 1 over s plus 1 plus 1 over s minus 1. Now, if I want to perform the inverse Laplace transform, I can. These actually do fit with table values that we have. If you remember that, and again, this is where that familiarity will come into play, because in your table, we have the Laplace of e to the alpha t is equal to 1 over s minus alpha. And that's where this fits into that, okay? So basically, the way this looks is that I perform the inverse Laplace to everything. I take the inverse Laplace of capital F of s, and I take the inverse Laplace of 1 over s plus 1, and I do it to 1 over s minus 1. All right, and using this fact right here, it looks like, obviously to take the inverse Laplace of capital F of s, I would get lowercase f of t, which is what we wanted. right here, going back to my transform from my table here, it looks like this would be an alpha of -1. And it looks like right here that this would be an alpha of +1. And so performing those inverse transforms means that this would be e to the -t for the first term, and this would be e to the +t, and that would be my lowercase function f. Now, what you will see as well is like these both had a nice numerator of 1. If they had a numerator of any other constant, 2, 3, some kind of constant, then what would have happened is something like our previous example where we had a constant out in front. And then that would just end up going to your numerator, or you would pull it from your numerator and it would, end up being a coefficient probably on that term then. So these didn't have any coefficients other than 1, which made them kind of nice, but that is my lowercase function f. So definitely work with your inverse Laplace transforms. They're very tricky. And I just wanted to include here for you to write down. If you want to stop this video now, you can. I'm just going to go through the transforms that we've learned thus far, so you can make sure you have those. And like I said, I will also be linking a document with a table on it. So first things first, the Laplace of 1, we got 1 over s. Then we did the Laplace of e to the alpha t. We got 1 over s minus alpha. Now, I can't remember too, and I'm just saying this now, if your book uses alpha, it might use k instead. So just be aware of that. And then the Laplace of t, we got 1 over s squared. The Laplace of t to the nth, we derived. And we got n factorial over s to the n plus 1. All right, and then our trig functions, the Laplace of sine of omega t. We have omega over s squared plus omega squared. I did tell you the table would have cosine. I'll go ahead and include that here as well. The Laplace of cosine of omega t is equal to s over s squared plus omega squared. Very close. And then the ones that we added on in our last video are the first derivative, f prime of t, which is s times the Laplace of f of t minus f of 0, and the Laplace of f double prime of t, which is s squared times the Laplace of f minus s times f of 0, multiplication, minus f prime of 0. Okay, so those are the ones we've done thus far. Just have those somewhere close by that you can reference. If you can't print the table that I'm going to post, then definitely just make one for yourself and keep that while you're working on the homework. Let me know if you have any questions, and if not, have a wonderful weekend.